Sorry, so if we go on if one simulates uniformly along this axis and then compares and counts the number of values in this vector that are smaller than this value here, then you get the probability of getting, for example, 5 of this is equal to the difference in height between those two, and that will be exactly equal to the probability of observing 5 in this binomial distribution. So if you look at it, this algorithm works. And similar for this Poisson algorithm. So, okay, so let's go back to the presentation. So this works for any random variable that has a small number of possible values. If it has an infinite number, you can always compute the probability of being above a certain value, and if you simulate that, then you can, afterwards compute the probabilities of being above that limit and so on. So there are algorithms to compute this efficiently when you have discrete distributions. Another way of simulating the continuous distributions, when you have, this is inspired by the drawing we just made. So let's say that x is a random variable with an invertible cumulative distribution function. And if u is uniform from 0 to 1, then f inverse of u is a random sample from x. So this may be obvious to you, but maybe we'll just try to draw it. So let's say that you have some kind of density that looks like this. Now the cumulative density of the cumulative distribution function, just the integral of this, will look then something like this. So it will approach 1 up here. So then if you simulate uniformly along this line here and take so this is the f function, and then you take the inverse of that one. That means that you start here and you get to the inverse of, so sorry, this should be f of x, and then this is u, and then this would be f inverse of u. Now you can see that you will get values that are basically distributed as this density, because there will be most when this density is high and very few when the density is low. So that's the intuition behind this. You can then compute it if you like. You can say that the probability that this inverse transform of a uniform variable is less than alpha, just by applying f and then solving this, you see that this particular random variable has a cumulative distribution that is exactly the one that you want. So that's a proof that this method works. As an example, the exponential distribution has density pi of x is equal to lambda x of minus x lambda. And if you integrate this function, then you get the cumulative distribution function that is of this form here. And now you can see that if you write f of x equal to u and solve with respect to x, you get this inverse function here. So if you apply this inverse function to a random variable u that is uniform, you get something that is exponentially distributed. Now, so you can put in a uniformly distributed u here and take 1 minus it, but then you still get something that's uniformly distributed. So you can replace this with the u, and then this is the most efficient formula to apply to this uniformly distributed U to get something that is exponentially distributed. So this can be expanded in many cases. Let's have another example, logistic distribution. It can be defined in itself by defining its cumulative distribution function. Unless you have specific parameters, this is what it looks like. And of course, if you say that this should be equal to some U and then solve for X, you can see that, well, there's only one X there. It's easy to solve for X. And you get some invert, you get a possibility to invert this function. Another example is a Cauchy distribution, which has this density. Integrating it gives you this cumulative distribution function, and again, it's easy to invert. So whenever you can invert this function, you have a very easy way to simulate from the density. So another way to generate random samples is to transform them, to simulate from some distribution and then do some calculations, and you get something that you can prove has another distribution that you would like. So one example of this is that you can prove that if this is now a random sample from the exponential distribution with parameter 1, so we just saw how to simulate from this, so we know how to do that. Well, then if we take the sum of these and multiply with the beta, then this is gamma distributed with parameters n and beta. So now suddenly we can, building on the exponential distribution, we can now simulate gamma distributions, at least where this first parameter is an integer. Another example, you can prove that if this is a random sample that with exponentially distributed variables, if we just sum the first A of those and divide by the sum of the first A plus B, then you get something that is beta distributed with parameters A and B. So now you can simulate from the beta distribution where A and B are integers at least. And another thing is that you can prove if U1 and U2 is a random sample from the uniform distribution, then this particular transformed vector is a random sample from a bivariate normal distribution. So you can actually get now from this uniform sample, you can get a bivariate normal distribution, and then each of the components of this vector will then be a normally distributed variable. So now you can simulate from the normal distribution also, building on this. Okay, so these are mainly examples that you will see maybe some more of in exercises. But in order to do so, you need to be able to understand how you transform the densities for random variables when you apply a function. So let's just review that, both for the univariate case and the multivariate case. So recall from basic probability theory that if f of x is a density function, and if now x is expressed as another function of y, where h is then a monotone transformation, then the density function for y has this expression. So we're not going to go back into the basic probability theory. You can look it up and you will find something similar to this expression there. So remember that now x is expressed in terms of y. And if that means that we have a density for x, and in order to then get the density for y, we have to, if y is expressed as the inverse of h applied to x, then you get this density. So if we apply the inverse of h to a variable with known density, we get the density of the resulting variable using the formula above. So let's have one application. It's kind of strange, but it's nice also. So remember that the non-informative prior for the precision parameter tau of a normal distribution is the improper distribution with density. So it's not a real density because it's an improper density. It's proportional to 1 over tau. Now, tau is the precision, so that's 1 over the variance. Now, what would be the non-informative prior for the variance, one might ask. So you can use this theory to get that, because if tau is now h of sigma squared, which is 1 over sigma squared, this is the relationship always between the precision and the variance. So then h of x is 1 over x. And the derivative of that is minus 1 over x squared. So now we can plug into this formula using tau as x and sigma squared as y. And basically this is, you just plug into this formula and you get this thing here, and it solves to 1 over sigma squared. So maybe counterintuitively, if you transform from the tau improper density to the sigma squared improper density, it has exactly the same form, 1 over sigma squared. So that's nice in a way also. Let's end with a transformation of multivariate random variables. So if x is a vector and if f of x is a multivariate density function, and if x equals h of y is a bijective differentiable transformation it should be, then the multivariate density function for y is has basically the same form. Now it's not the derivative, now this is the determinant of the Jacobian matrix. So if you know some multivariate analysis, then you will recognize this. And you can apply this in a similar way. And one application of this is in the proof of the formula used above to sample from the bivariate normal distribution. But we'll not go into this. We'll just mention that this is an important ingredient when you're going to do this for multivariate distributions. Okay, that's it for now.